This multi-flash photograph shows two pool balls, each of diameter 6 centimeters, photographed at a rate of 25 frames per second. Initially, one ball is at rest, that's the dark one, and the other ball is entering from the left. The two balls collide and move off to the right. The first task is to draw a vector v sub I that represents the velocity of the incoming ball. The main concepts involved for solving this problem are interpreting motion diagrams such as this, making estimates from such diagrams, and understanding the definition of velocity. In the problem statement, we are told that the incoming ball is entering from the left and moving towards the right towards a stationary ball that's colored dark. We are asked to draw a vector, v sub I, that represents this motion. The two things a vector needs are a direction and a magnitude. So, because this ball is coming in this direction, the direction of the vector vi should also point in this direction, left to right. The magnitude of v sub I is proportional to how fast the ball is moving, and can be written in this formula here, where velocity is equal to the change in distance divided by the change in time. With these two ideas in mind, we draw the following vector here. It is in the same direction as these frames here show, and its magnitude, as we will see later, is proportional to the spacing of the ball. In part B of this question, we are asked to draw two vectors, v1f and v2f, that represent the velocities of each of the outgoing balls after the collision. The first thing we'll do is label the two balls. We will call ball 1 the incoming ball that then goes in this direction after the collision, and ball 2 the stationary ball which then goes in this direction after the collision. In order to draw the vectors v1f and v2f, we will need to know both the direction and the magnitude of each of these vectors. The direction of a velocity vector is the direction of motion, so for v1f, this will point down and to the right as shown in this picture, and for v2f, it will point up and to the right as shown in that picture. The magnitude of the velocity vector is equal to the displacement divided by how long it took for that displacement to occur. In this picture, each of these circles represents where each of these balls were at a given instant. This diagram here shows the position of each ball at a specific moment in time. We also see that the incoming ball travels a greater distance than either ball 2 or ball 1 in the span of one time frame. From this information, we can conclude that the vector v sub I, which was the velocity of the incoming ball, has a bigger magnitude than the vector v sub 2f, the velocity of ball 2 after the collision, which has a bigger magnitude than v sub 1f, the velocity of ball 1 after the collision. We know this because in the span of one time frame, the incoming ball travels a greater distance than ball 2 travels a greater distance than ball 1, so the ordering has to be like this is shown here. Now that we know the direction and the relative magnitudes of the vectors v1f and v2f, we can finally draw them here. v1f points down and to the right in this direction, v2f points up and to the right in this direction, and the length of v1f is shorter than the length of v2f. In part C of this question, we're asked to show graphically that v sub I, the velocity of the incoming ball, is equal to the vector sum of v sub 1f plus v sub 2f, the velocity of the ball 1 after the collision, and the velocity of ball 2 after the collision. To prove this statement, we first add the vectors v1f and v2f by aligning them head to tail and drawing the resultant vector. For two vectors to be equal, they need to have both the same magnitude and direction. If we were to compare the magnitude and direction of this resultant vector formed by adding v1f and v2f, we would see that it has both the same magnitude and direction as the vector we drew in part A. This is proof graphically that v sub I is equal to v1f plus v2f. In the bonus of this question, we were asked to calculate the relevant quantities from the photograph and prove that the magnitude of v sub 1i squared is equal to the magnitude of v1f squared plus the magnitude of v2f squared. To find the magnitude of each velocity, we need to estimate how far each ball travels in between each frame and then divide this by the frame rate. So we'll have velocity is equal to displacement divided by time. We are told in the problem statement that the diameter of each ball is 6 centimeters. We can use this information to estimate the distances between each ball in between frames. For the incoming ball, it looks like the ball travels 1, 2, and roughly 1/3 ball diameters in between these two frames. Therefore, the displacement for the incoming ball would be 2 1/3 ball diameters times 6 centimeters, because each ball diameter is 6 centimeters across, to give us roughly 14 centimeters. For ball 1, it looks like the ball travels 1 ball diameter in between the two frames. The displacement for ball 1 is therefore 1 ball diameter times 6 centimeters to give a displacement of 6 centimeters. For ball 2, it looks like this ball travels 2 ball diameters in between these two frames. The displacement for ball 2 is then 2 ball diameters times 6 centimeters to give us roughly 12 centimeters for the displacement. At this point, we know the delta R for each of the 3 balls. We need to calculate now delta T, that is, the time it takes for the incoming ball to go from here to here, for ball 1 to go from here to here, and ball 2 to go from here to here. We are told in the problem statement that the frame rate is 25 frames per second. That means the amount of time that elapses between this frame and this frame is 1 divided by 25 seconds to give us a time of 0.04 seconds. To finish the problem, we rewrite this equation in terms of displacements and times and plug in each of these numbers that we calculated. After converting our numbers to meters squared per second squared, we find that v sub I squared is roughly equal to 12.25 meters squared per second squared, and that this sum here is roughly equal to 11.25 meters squared per second squared. These two numbers are roughly the same. The discrepancy is coming from our coarse estimate of the displacements for each ball. If we had been more careful about measuring the displacements, we would see these two numbers would agree much more than they already do.